An object from another star system arrives, not following the standard playbook. 3. I-Atlas, the third interstellar visitor we have ever confirmed, discovered July 1st, 2025 by the Atlas Survey Telescope in Rio, Hurtado, Chile. But this one does something comets are not supposed to do. It spins jets toward the sun, it wobbles like a lighthouse beam, and its rotation cycle syncs with morphological changes that astronomers cannot fully explain using the models built from 60 years of studying comets born in our own system. A rotation pattern locked to emission structures that point the wrong direction and stay collimated when they should spread. Additional data comes from Tony Santana-Rose and team publishing rotation period measurements in August 2025 using coordinated observations from multiple telescopes between July 2nd and July 29th. Hubble Space. Telescope imaging data released by NASA and the European Space Agency on August 7th, 2025, and reanalyzed in November and December by David Jewett at UCLA. James Webb Space Telescope spectroscopy from August 6th, 2025, showing carbon dioxide, water, and carbon monoxide emission rates. And continuous tracking data from the Minor Planet Center, compiling 4,022 astrometric observations from 227 observatories worldwide between May 15th and September 23rd, 2025. If you value documented astronomy and interstellar object research like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. This script is researched and factual using sources from the Astronomy and Astrophysics December 2025 edition featuring Sarah Ricart-Licandro and Alarcon's Wobbling Jet Study, and the August 2025 Or-Archiv preprint by Jewett. Colleagues constraining nucleus size through Hubble decomposition methods that separate coma light from the unresolved core. Now back to the information. That speed is 70% faster than anything gravitationally bound to our star. Is trajectory bent into a hyperbolic arc, eccentricity greater than 1. It will pass the sun once and never return. But the trajectory had one feature that made astronomers double-check the numbers. The path aligned to within 5 degrees of the ecliptic plane, the flat disk where all 8 planets orbit. For a random interstellar intruder, the chance of that alignment is 0.2%, 1 in 500. On July 2nd, 2025, the Minor Planet Center gave it the designation 3i, third confirmed interstellar object, and the cometary designation C/2025 N1. By the time it was officially named, the center had collected 122 observations from 31 observatories. David Jewett and Jane Liu observed it with the Nordic Optical Telescope on July 2nd and confirmed clearly active with diffuse appearance. Hubble captured it on July 21st, 2025, when the comet was 277 million miles from Earth. The image showed a teardrop-shaped cocoon of dust, but the plume extended in the wrong direction. Position angle 280 degrees, plus or minus 10 degrees, about 180 degrees from the anti-solar direction. Some comets show antitails when Earth crosses their orbital plane, and perspective makes trailing dust appear sunward. But multiple analyses confirmed 3I Atlas displayed a real sunward jet, not geometric illusion. The structure remained across different viewing angles and dates. By late August, the comet developed a normal anti-solar tail as solar radiation took over. But the inner coma within 5 arcseconds of the nucleus stayed fan-shaped and brighter on the sun-facing side. Images from August 26th, 2025 showed this clearly. Period of 16.16 hours plus or minus 0.01 hours. The variations decreased from 0.3 magnitudes to 0.2 magnitudes throughout July. The fading amplitude likely meant the nucleus was becoming more obscured as activity increased and the coma thickened around it. You need something fixed to the surface that appears, disappears, and reappears as rotation brings it into sunlight, then shadow. The jets provided that structure. Miquel Serra Ricart, scientific director of Light Bridges, and Javier Licandro at the Instituto de Astrofísica de Canarias, led a campaign with the 2-meter twin telescope at Teide Observatory in Tenerife. 37 nights of observation. July 2nd through September 5th, 2025. They tracked the inner coma, not just brightness, position, orientation, shape. The wobble period measured 7.74 hours, plus or minus 0.35 hours. Exactly half the rotation period measured from brightness. If a single active spot near one of the nucleus poles vents gas and dust, then as the nucleus completes one full rotation, that spot crosses the sunlit side twice, once per hemisphere. The jet appears, wobbles, and reappears. 7.74 hours times 2 equals 15.48 hours, plus or minus 0.70 hours. The rotation period derived from jet precession matched the brightness period within error bars. The team measured position angles of the jet at a projected distance of 6,000 kilometers from the brightness peak. When they phased the position angles with a 7.74-hour period, the data collapsed onto a sine curve. The mean position angle representing the sky projected orientation of the rotation axis stayed constant. The jet wobbled around it. This was the first periodic jet angle modulation ever detected in an interstellar object. Solar system comets show jets. Some wobble. But this was an object formed around another star showing the same physics. Rotation drives asymmetric outgassing. Outgassing creates jets. Jets precess if misaligned with the spin axis. The pristine body arrived carrying volatiles that sublimate under solar heating, just like native comets. But there were differences. Projection factor 1 over sine 10 degrees equals 5.8. Actual length to width ratio, 11.6. Tightly collimated out to distances exceeding 500,000 kilometers, larger than the Earth-Moon distance. Images from December 15, 2025, processed by Tony Scarmato using Larsen-Sekanina gradient filters, showed the anti-tail still extending sunward. Field of view, 1.6 million by 0.7 million kilometers. The jet remained narrow, opening angle unchanged. Analysis by Avi Loeb at Harvard suggests dust grains in the anti-tail have characteristic radius around 10 micrometers. Using the observed jet length and requiring that dust reaches jet speed through drag on outflowing gas, Loeb derived gas mass density D approximately 3.2 times 10 to the minus 8 grams per cubic centimeter times distance from nucleus center D in kilometers to the minus 2 power. These values allow calculation of particle number density and scattering probability. The dust blanket surrounding 3I Atlas sits on the borderline between opaque and transparent to sunlight. Probability of order unity. That balance between dust release and sunlight penetration may maintain the jet structure. Sarah Ricart and colleagues reported the jet base offset less than 8 degrees from the rotation axis poles. That geometry means, at large distances from the Sun, 3I Atlas has a steady day side and steady night side, which switch roles at perihelion. The rotation axis points nearly at the Sun. For a randomly oriented interstellar object, the chance of alignment within 8 degrees is 0.5%, 1 in 200. If the jet originates from a simple ice pocket sublimating under sunlight, the alignment constitutes what Avi Loeb calls the 14th anomaly. Why would the spin axis happen to point sunward when the object enters the inner solar system? The probability is low. Add it to the ecliptic alignment of 0.2%. Multiply the probabilities. 0.001%, 1 in 100,000. Either 3. IATLAS got extraordinarily lucky, or some mechanism we do not understand constrained its orientation. Late August transition as normal anti-solar tail develops, but inner sunward fan persists. September 7th, James Clerk. Maxwell telescope detects hydrogen cyanide production rate 1.5 times 10 to the 25th molecules per second at 2.33 astronomical units from Sun. September 14th, production rate climbs to 4.5 times 10 to the 25th molecules per second, 2 kilograms per second. Coma, 180,000 kilometers across asymmetric elongated antisolar. Dust tail 50 arc seconds wide, approximately 100,000 kilometers. October 29th, 2025 perihelion. Distance 1.4 astronomical units, 130 million miles, just inside Mars orbit. Speed 153,000 miles per hour. October 31st through November 4th, brightness increases by factor of 5 and green band wavelength 0.464 micrometers. November imaging by Francois Kugel shows bright nucleus with multiple directional jets and subdued traditional tail. Small deflection. If the rotation axis stayed fixed in space, the original sun-facing pole active before perihelion would now be on the night side, opposite the Sun. But Hubble images from December 12th and December 27th, 2025, released by NASA ESA STSCI, showed a double jet structure. One prominent anti-tail still directed at the Sun toward lower left, one weaker jet in a different direction. The relative brightness and projected shape of the two jets changed significantly between December 12th and 27th. As the anti-tail jet brightens, the opposite jet weakens. Expected from precession around a rotation axis. The wobble explains the heartbeat brightness changes observed with 16-hour period back in July. Heat conduction could transport excess solar energy from dayside to nightside over the perihelion passage. Sublimation on the new heated pole creates the observed post-perihelion sunward jet, but this requires the object to have volatile deposits positioned at both poles. Improbable, but not impossible. Processed images using Larsen-Sekanina rotational gradient filter revealed triple jet structure. Anti-tail, extending approximately 400,000 kilometers sunward. 2 additional jets positioned at equal angles relative to the anti-tail, all 3 rotating around the major anti-tail like the beam of a lighthouse. The symmetric configuration raised questions. How do 3 jets maintain equal angular spacing? How does the central antitail remain collimated and sunward through months of observation and gravitational deflection? Non-gravitational acceleration measurements from spacecraft, including Psyche and ExoMars, trace gas orbiter plus astrometric data suggest nucleus mass greater than 3.3 times 10 to the 16th grams. For bulk density, 0.5 grams per cubic centimeter. Typical of comets, this corresponds to diameter greater than 5 kilometers. Close to the upper Hubble bound. Mass loss rates from JWST observations. On August 6, 2025, nucleus emitting 129 plus or minus 1 kilograms of carbon dioxide per second, 6.6 plus or minus 0.2 kilograms of water per second, 14 plus or minus 0.9 kilograms of carbon monoxide per second, 0.43 plus or minus 0.09 kilograms of carbonyl sulfide per second. Total volatile production roughly 150 kilograms per second. Over 10 days, that equals 130 million kilograms. Over 100 days, 1.3 billion kilograms. Substantial, but not catastrophic, for a nucleus with mass 10 trillion kilograms or more. Likely amorphous ice, though crystalline cannot be ruled out. Swift observatory tentative detection of water vapor and hydroxyl radicals on July 31st and August 1st, 2025, suggested ice grains sublimating beyond the nucleus. Distance between 4,000 and 10,000 kilometers from center. Dust particles in coma show size distribution. Small grains, 1 micrometer radius, ejected at 22 meters per second. Large grains, 100 micrometers radius, ejected at 2 meters per second. The size sorting affects how radiation pressure shapes the coma and tail. 3I Atlas, at 2.33 astronomical units, already releasing significant carbon dioxide, suggests it formed far from its parent star beyond the carbon dioxide frost line where temperatures stay below 120 Kelvin. The high carbon dioxide to water ratio implies formation in a cold outer disk region, possibly a planetary system around a star with lower metallicity or different carbon to oxygen ratio than the Sun. The galactic velocity vector points to origin in the thick disk, not the thin disk. Velocity components, UVW equal minus 51, minus 19.2 plus 18.5 kilometers per second in galactic coordinates. The thick disk contains older stars with lower metallicity formed early in galactic history. If 3I Atlas comes from a thick disk protoplanetary disk, it could be billions of years old, possibly 11 billion years. Ancient ice preserved in interstellar space until encountering our Sun. The surface reddish color, similar to D-type asteroids and solar system comets, likely results from irradiated organic compounds called tholins in the coma. But beneath that outer layer, fresh ice remained. Upon solar heating, the ice sublimated and dust lofted into the coma. 67P Churyumov-Gerasimenko rotates every 12.4 hours with nucleus 4 kilometers across. 1P Halley rotates every 52 hours with nucleus 15 by 8 kilometers. But faster rotation is not unprecedented. Some asteroids and comet nuclei spin in hours. The wobble mechanism requires asymmetric outgassing, creating torque. Yet, analyses from July through September showed no detectable non-gravitational acceleration at 3 sigma confidence using 4,022 data points. Either the outgassing was symmetric enough to produce no net force, or the nucleus mass was large enough that the force was below detection threshold. Value reduced by 1/3 relative to earlier upper limits, but detection stood at 3.7 standard deviations, measured at 1.38 astronomical units. The acceleration implies increased outgassing after perihelion, more mass loss, larger coma. But November 11th, images by multiple observers showed a single intact body, no evidence of breakup or fragmentation. Some estimates suggested the mass loss rate would equal the entire estimated minimum mass over the perihelion passage. Yet the nucleus remained coherent. Area is weaker than typical comets. The brightness data suggests over 90% of optical flux comes from the extended coma, not the solid nucleus. Models and observations agree the active coma dominates not the core, so the true nucleus size remains uncertain within the 440 meter to 5.6 kilometer range. Their structure, origin, and evolution encode information about the nucleus shape, spin, state, surface composition, and internal structure. Cometary jets typically form when localized areas of the nucleus surface sublimate faster than surrounding terrain. Could be fresh ice exposed in a crater or cliff, could be a depression that focuses sunlight, could be a compositional boundary. On 3, I Atlas, the jets activate when specific regions rotate into sunlight. The 7.74-hour wobble period equals half the rotation period, meaning the active spot crosses the sub-solar point twice per rotation. Once near each pole, gas expands outward at thermal speeds around 400 meters per second for water vapor. Dust entrained in the flow gets lifted. The gas and dust plume spreads, creating a cone, For 3, I-Atlas. The anti-tailjet is collimated and points toward the sun out to 1 million kilometers. At thermal speed, 400 meters per second, it takes roughly 1 month for material to traverse 1 million kilometers. Yet the jet orientation stays stable over that time, despite nucleus rotation every 15.5 hours. If the valley happens to align with the rotation axis and the axis points at the sun, the jet appears sunward and precesses minimally. This requires fine-tuning of topography, orientation, and axis alignment, but could occur naturally. The puffs string out in space like beads on a wire. Separation between puffs equals velocity times period. 400 meters per second times 15.5 hours converted to seconds equals about 23,000 kilometers. Over 1 million kilometers, that gives roughly 43 discrete puffs. Imaging might resolve them as structure within the jet, but requires sub-arc second resolution. At 3, I-Atlas distance in December 1 arc second equals several thousand kilometers, marginally resolvable. As rotation brings each feature into sunlight, it activates creating a jet. The jets rotate around a central axis, producing the lighthouse effect. But maintaining 3 jets with equal angular spacing over months while one dominates as antitail requires precise geometric arrangement. Particles scatter sunlight most efficiently in the forward direction. If the dust coma is optically thick and extended forward, scattering enhances brightness toward the sun, creating the appearance of a sunward tail, even if particles physically trail the nucleus. But analyses of the brightness distribution and spectral properties argue against pure scattering geometry. The antitail shows structure, narrow collimated features, not diffuse forward scattered glow, unlikely to collimate a jet over 1 million kilometers. Analysis suggests initial speeds 30 to 120 meters per second for plausible radiation pressure parameters, lower than typical thermal speeds, but higher than the 5 meters per second inferred from standard coma models. The dust population appears dynamically extreme, high speed, possibly collimated by jet geometry or magnetic fields or some other mechanism. Retrograde trajectory aligned to ecliptic within 5 degrees. Probability 0.2%. Rotation axis aligned to sunward direction within 8 degrees. Probability 0.5%. Combined probability 0.001%. Arrival timing brought 3 I-Atlas within 29 million kilometers of Mars and 54 million kilometers of Jupiter at specific dates, while being unobservable from Earth during perihelion due to solar conjunction. Fine-tuned geometry, nucleus size and mass loss rate and tension, collimated sunward jets before and after perihelion despite 16-degree gravitational deflection. Triple jet structure with symmetric spacing, possibly around a low metallicity star in the thick disk billions of years ago. Different volatile ratios, different formation temperature, different parent body size distribution. These factors could produce a comet that behaves similarly to solar system comets in most ways, but shows statistical outliers in geometry, rotation, and jet structure. With only 3 confirmed interstellar objects detected, and only 3 I-Atlas showing strong activity, we lack the population statistics to say what is typical for interstellar comets. But no radio emissions above background were detected by breakthrough LISTEN observations using Green Bank telescope during closest Earth approach on December 19th. No candidate signals. The object exhibits mostly typical cometary characteristics, including coma nucleus and unelongated shape. The chemical composition matches expectations for volatile-rich bodies. No evidence for artificial materials or propulsion. The debate centers on interpreting low-probability events. In a large enough sample, unlikely things happen. Over billions of years and trillions of potential planetary systems, some fraction of ejected comets will have unusual orientations. Observer selection bias matters. We detect interstellar objects when they pass close enough and bright enough. 3. I-Atlas was discovered because it became active, producing a coma that boosted its brightness. An inactive object of similar size would have escaped detection. So the sample is biased toward active comets, and we have no baseline for typical interstellar comet properties. Spectroscopy can reveal which volatiles dominate post-perihelion and whether the interior differs from the surface. Ground-based telescopes worldwide continue imaging. Every data point refines the rotation period, jet morphology, nucleus size, and mass estimates. Closest approach to a giant planet. The gravitational perturbation is small but measurable. Tracking the trajectory before and after Jupiter encounter allows precise determination of the object mass from how much Jupiter deflects it. Then, we will know if the nucleus is closer to 440 meters or 5.6 kilometers. Speed it entered. 58 kilometers per second relative to the Sun, faster than any other confirmed interstellar object. 1 I-Oumuamua moved at 26 kilometers per second, 2 I-Borisov at 32 kilometers per second, 3 I-Atlas at 58 kilometers per second. Its high velocity and thick disk origin suggest great age and long interstellar journey. possibly traversing the galaxy for billions of years before this brief encounter with our sun, never returning. But the hyperbolic trajectory carries it back into interstellar space. In thousands of years, it will be light years away. In millions of years, halfway across the galaxy. Perhaps the first time in billions of years. The ice that formed in a protoplanetary disk around an ancient star now sublimates under our sun. The dust that condensed in that distant nebula now scatters sunlight, creating the coma we observe. Jets precess because the active spots sit offset from the spin axis poles. The mechanism is solid physics, documented in solar system comets, confirmed in the interstellar visitor, but the extreme collimation and persistent sunward orientation push the boundaries of standard comet models. In evolutionary paths, ice-dominated nuclei, volatile mixtures dominated by water, rotation rates distributed across a range, outgassing that creates symmetric comas or modestly asymmetric jets, radiation pressure and solar wind shaping the tail in predictable ways. 3. I-Atlas fits most of those patterns, but deviates in key details. They demonstrate that comets can form under conditions different from our solar system and behave differently when activated. The study of interstellar objects is the study of comparative planetology. How do planetary systems around other stars differ? How does chemistry vary with stellar metallicity? How do formation distances and disk properties affect comet composition? How do dynamical ejection mechanisms select which bodies escape? Each interstellar visitor provides one data point. 1I Oumuamua, unusual shape, no detected activity, anomalous acceleration, still debated. 2I Borisov, classic comet appearance, water and carbon monoxide, fragmented near perihelion, similar to solar system comets. 3I Atlas, high carbon dioxide, unusual rotation in jets, tightly collimated antitail, geometric coincidences, each one different, each one expanding the parameter space. The population of interstellar objects passing through the inner solar system is estimated at 0.1 to 1 per year, based on detection rates and survey completeness. Most go undetected. Too small or too faint or wrong timing. Discovery requires the object to be bright enough when close enough and observable from Earth. 3I Atlas met those criteria. Its activity boosted brightness. Its trajectory brought it within observable range during northern summer, when major telescopes had access. Its timing aligned with an era of advanced surveys and rapid response networks. Comparisons with future interstellar objects will test whether 3I Atlas is an outlier or represents a common class. Every new visitor provides a comparison point. With 3 objects, we see hints of diversity. With 10, we might discern patterns. With hundreds, we could map the parameter space of interstellar small bodies. The rotation of an interstellar nucleus spinning every 15.5 hours. The jets wobbling every 7 3/4 hours. The sunward anti-tail collimated to 8 degrees over 1,000,000 kilometers. The morphology shifting from single jet in July-August to double jets in December to triple jets in January. The carbon dioxide, water, and carbon monoxide sublimating from ice that formed around another star billions of years ago. The story of 3. I-Atlas is written in the light. Photons reflected from dust grains in the coma. Photons absorbed and re-emitted by gas molecules fluorescing in ultraviolet sunlight. Photons carrying spectral signatures of water ice, carbon dioxide, and organic tholins. Photons captured by telescopes on Earth, in orbit around Earth, and en route to other planets. Each photon a messenger from the interstellar visitor. Together they spell out the physics. The sunward direction tells us the rotation axis points at the sun, at least during the observation window. The persistence tells us the axis stays stable despite torques from outgassing. 1I Oumuamua, small and active, possibly elongated. 2I Borisov, active, fragmenting water rich. 3I Atlas, large, highly active carbon dioxide rich. 3 data points, widespread. The 4th interstellar object, whenever it arrives, will add another point. Over time, the picture will sharpen. The rotation data and jet morphology recorded in 2025 are irreplaceable. The window to observe closed as the object receded and dimmed. What we learned stays. 15.5-hour rotation period, 7.74-hour precession period, jets offset by less than 8 degrees from rotation axis poles, antitail collimated to 6 to 8 degrees, persistent sunward orientation, nucleus diameter between 440 meters and 5.6 kilometers, carbon dioxide production 129 kilograms per second, water 6.6 kilograms per second, mass greater than 3.3 times 10 to the 16th grams, velocity 58 kilometers per second relative to the sun. Thick disk origin, possible age 11 billion years. They prevent speculation from drifting into fiction. They force models to match observations, not wishes. They document the behavior of an object that formed in another star system, traveled through interstellar space for possibly billions of years, and briefly interacted with our sun before departing forever. Documented by 37 nights of continuous observation with the 2-meter twin telescope at Tidy Observatory between July and September 2025. Published in Astronomy and Astrophysics, December 2025. Rotation period derived from brightness variations by Santana Rose and colleagues, published August 2025. Jet wobble period and precession analysis by Sarah Ricart, Licandro, and Alarcon at the Instituto de Astrofísica de Canarias. Nucleus size constraints from Hubble Space Telescope. Imaging by Jewett and team released August and reanalyzed November, December 2025. Composition measurements from JWST NIR spec observations, August 6th, 2025, released by NASA, August 25th. Astrometric data from Minor Planet Center compiling observations from 227 observatories. All sources are public peer-reviewed or preprint manuscripts accessible through NASA Archives, IAC Communications, and the Archive repository.